Hey everyone, and welcome. So today we're diving into something about science that sounds, well, just completely backward. It turns out that the most powerful, game-changing scientific theories are often the most improbable ones. I know, right? How can the biggest long shots possibly be our best bets for learning about the universe? Let's get into it, because this paradox is really the secret sauce of scientific progress.
So let's just start with a really basic question. When you think about a rock-solid scientific theory, something like relativity or evolution, what do you think makes it so strong? What's the very first thing that pops into your head? I'm willing to bet that if you're like most of us, your answer is going to be something along these lines. A strong theory is one that's just really, really likely to be true. It has a super high probability of being correct. And that makes perfect sense, right? It feels like the most obvious, common sense answer. And that gut feeling we all have, that goal of finding theories that are probably true, it's not just a hunch. It's actually been formalized into a whole branch of logic that's dedicated to doing exactly that.
This field is called probability logic. And, no surprise, its main goal is to figure out which theories have the highest probability of being true. It's all about finding the safe bets, the ideas that are so heavily backed up by the evidence we already have that they're almost guaranteed. It's a hunt for certainty.
That sounds pretty smart, right? Very logical, very reasonable. But here's the big twist. Is that safe probability-first approach, is that really what scientists are doing when they're out there pushing the absolute boundaries of what we know? Well, it turns out that on the frontiers of discovery, scientists really aren't looking for safety. Nope. They value something totally different. They have a completely different way of measuring a theory's true worth. And that something is what we call empirical content. Now, here's the mind-bending part. A theory's content isn't measured by what it says can happen. It's measured by everything it says cannot happen. A really powerful theory is super restrictive. It makes bold, specific claims that rule out tons of other possibilities. And this slide just lays it out perfectly. Look at the low-content theory on the right. It might rain somewhere, sometime. I mean, it's so vague, it's almost guaranteed to be true, right? But it's also not very helpful. Now look at the high-content theory. It will rain in this specific place tomorrow at exactly 2 p.m. Wow, that theory asserts a lot, and it forbids every other outcome. It's incredibly risky, but if it's right, it's unbelievably informative. Okay, so now let's connect those two big ideas, high content and probability. This is where it all clicks together, and we see how science actually gets a huge advantage from what looks like a weakness, improbability. When you really think about it, the logic is kind of unavoidable. Okay, follow me here. More content means you're making more specific claims, right? And the more specific your claims are, the more chances there are for you to be wrong, more ways for someone to test your idea and prove it false. And logically, the more ways there are for you to be wrong, the lower your initial probability of being 100% correct has to be. Which leads us to this wild conclusion. The theories that are the most powerful, the most informative, the ones with the absolute most empirical content, they are by their very nature the most improbable. They are the biggest logical long shots you can possibly imagine. And just how improbable are we talking about? Well, for any universal law, think the law of gravity, which says it works everywhere in the universe for all of time, its logical probability of being true is, for all intents and purposes, 0. Yeah, not close to 0. It's 0. It makes an infinite number of claims, so its chances of being right from the get-go are basically none. So if science isn't chasing probability, what on earth is it chasing? If a theory starts out with a probability of 0, how does it ever become valuable? The answer is incredible. Its value doesn't come from its starting odds. It comes from how it performs under extreme pressure. And this is where we meet the hero of our story, corroboration. Now, corroboration is not a probability score. Think of it more like a report card or maybe a badge of honor. It's a summary of how a theory has faced down the toughest, meanest, most severe attempts to break it and has somehow managed to survive. So what makes a test severe? Well, it's not about just collecting another easy example that fits the theory. No way. A severe test is a targeted strike. It's a clever experiment designed to go right for the theory's jugular, its boldest, most specific, most unlikely predictions. You're not trying to pat it on the back. You are genuinely trying to prove it's wrong. And this quote just nails it. A theory doesn't get strong by collecting a million attaboys. It gets strong by surviving a handful of really, really difficult challenges. Challenges it had absolutely no business surviving. It's all about the quality of the testing, not the quantity of the evidence.
So what we really have here are two completely different mindsets, two fundamentally different ways of thinking about knowledge. It's a head-to-head matchup between the goals of the working scientist and the probability logician. And this table just lays it all out. Look at the primary goal. The logician wants high probability, safety. The scientist wants high corroboration, battle-tested strength. This leads to what they see as the ideal theory. For the logician, it's something low content and safe. For the scientist, it's a high-content theory that's bold and risky. They even measure success differently. One is about piling up evidence, the other is about surviving attacks. It really boils down to what they value most: justification and certainty versus boldness and falsifiability.
I know, this is all a little bit abstract, so let's use a quick analogy to really make this idea stick. I want you to imagine that a scientific theory is like a security system designed to protect a bank vault.
Okay, so the probability logician comes in and suggests a simple padlock for the vault. It's highly probable it will stay secure, but mostly because it's not protecting much and no serious thief is even going to bother. That's our low-content safe theory. The scientist, on the other hand, designs an insane, state-of-the-art fortress. We're talking lasers, pressure plates, biometric scanners, the whole shebang. Logically, it's highly improbable that every single one of those complicated parts will work perfectly without a single glitch. This is our high-content, low-probability theory. Then, what do? They hire the best safecrackers in the world to try and break in. Those are the severe tests. And when that complex, improbable system survives every single expert attack, that's when we know it's worth something. That is high corroboration. So when you get right down to it, science isn't a quest for certainty. It's a quest for the boldest, most informative, most testable ideas we can possibly dream up, and then a relentless, ruthless effort to prove those ideas wrong. It's the theories that survive that trial by fire that really teach us something new about the universe. Which kind of leaves us with one last thought, right? If science isn't about finding the final, certain truth, then maybe it's about something even more exciting: a perpetual quest for better and better questions.